Good morning, ladies and gentlemen. Today we are going to come back and look at the concepts of association and correlation. Previously, when we were discussing association, we were using it interchangeable with correlation, and that is actually incorrect. Though the two words are related, they do not mean the same thing. So as we start this discussion today, we're going to specifically be only using the word association, and you will see as correlation comes into play. So how do we measure the strength of an association? We previously talked about it could be weak, moderate, or strong. So if we're looking at these two variables in this scatter plot here, we have height versus weight, and we can clearly see a linear shape passing through this graph, maybe a little bit off there. And so we can clearly see it is linear. It is positive. And it has a strong association. Maybe even if you wanted to, moderately strong. And we can see here there is an outlier. So how do we measure? I mean, we can say moderately strong, we can say strong, and up to this point, that has sort of been a personal opinion. So how can we measure what that strength is? And and in measuring that strength, should that be dependent on the units of the variable? If we were to re-show this graph as maybe inches versus pounds, would the graph still look the same? So in discussing association and measuring it, let's remove the units from play. So instead of using inches and kilograms or centimeters and kilograms, we can use standardized values. Okay? Basically, Zx, Zy, the standardized of each of our variable, using the standard deviation formula, or the z-score formula. And my pen has stopped working again. Okay, so back in this. We're looking at, so here we have the classic z-score formulas, and we'd apply it to each variable and convert all of our ordered pairs into z-scores. And you can see the plot here. We can still see the positive correlation, or sorry, positive association. We still see the positive direction. You can still see the strong or moderate. Or moderate association. And I keep pushing my buttons. And the outlier, a little more present. The outlier is still a little bit more obvious. And we can see that. And you can see as this graph has been, should look a little steeper than the previous one. It looks steeper. But that is mostly due to how we change the scaling of the axes. Now we're scaling by standard deviation, so the scales on both axes appear to be the same due to equal scales, which was not true originally. All right, and it is from this idea of z-scores that we can then get this measurement of the strength of association, and that is what we call the correlation coefficient. The correlation coefficient provides a numerical before we've been using descriptive, strong, moderate, weak. Measurement of the strength of a linear, has to be linear, correlation is only for linear, of the relationship between the explanatory and response variables. R is our correlation coefficient. And, basic formula, the sum of the products of each ordered pair divided by roughly their quantity, n minus 1. Again, going back to standard deviation and being a population, we'll explore why it's n minus 1 and not n later on this year. Okay, this is the formula, and we're not going to calculate the span. Like standard deviation, it is a very cumbersome formula to use. We're going to use the calculator, but I wanted you to see it. Now understand, correlation measures the strength of linear associations. It only works between linear associations, and it only works for quantitative variables. So at this point now, we've only been saying association, and we need to only be saying association. Backtracking from what we did earlier this week, but only using association. And if we're going to use association, we are going to have to do correlation condition check before we can use the idea of correlation. It's going to be an issue right now, but you're going to get very used to doing condition checks. Almost every test we do, everything we're doing going forward will involve some type of condition check. And for a correlation condition check, there are three things. There's the quantitative variables condition. The variables must be quantitative. So variables must be quantitative. Be careful that we're not seeing categorical variables that are masquerading. Things like favorite numbers, things we talked about before, and they must be quantitative. We should know what's being measured. What is being measured? And in what units? Okay. Second condition we have is a straight enough condition. Remember, correlation only deals with linear associations. So see the scatter plot. Know that it is linear. Know strong associations could end up with very low correlations simply because it wasn't a linear association, so it won't have a good strong correlation, but it could still be a strong association. So remember, correlation is only for linear. And then outliers. Are there outliers? Outliers can play around with correlation. The presence of an outlier can increase or decrease correlation. So outliers can affect correlation. Depending on the information that we have, we may be able to calculate the correlation with or without the outliers, so we can compare to see the type of effect they're having. So as we're going to look through, anytime we're going to start to use correlation, and we haven't used still association, before we can switch to a correlation, it has to pass these three checks. They have to be checked off. If they do not, correlation is not an applicable measure, and we'll have to manipulate that. You'll see that in one-on-one examples of what we can do. Okay, so correlation, there are some properties that a correlation can express or model, and we look at them. The sign of the correlation, and we mentioned this a little bit earlier this week, the sign of a correlation demonstrates its direction. A positive correlation means we have a positive direction. The graph is increasing. Okay? Positive, increasing, negative, decreasing. Okay? Correlations, and we've talked to mention this before, correlations are between -1 and 1 inclusive. Okay? So they're between -1 and inclusive. Correlations can be perfect. It means R can be 1, R can be -1. They can be perfect. Not going to see that often in real world scenarios. That would mean everything lines up perfectly. Probably your exposure early on, they were much more perfect when we were doing it before. Real world, you normally don't see it. Remember that correlations that are near 0, correlations that are near 1 or -1, have strong associations, and correlations that are near 0 represent weak associations, and everything else in between. And we'll talk about more and more that means as we continue to explore it. Correlations are also symmetrical. Both variables are treated symmetrically. What that means is the correlation of x with y is the same as the correlation of y with x. The direction in which we calculate the correlation isn't going to change it. Correlations, because they are, as we said before, use calculation based on z-scores, correlations have no units. And correlations are not affected by changes in center or scale. So if we change it from inches to centimeters, the value of the correlation is going to remain the same. If we add some new data, so the center changes, still not going to affect the value of the correlation. Okay. Remember, they affect, as I said before, and this is where we've got to be crucial, they affect their strength of linear associations. Linear associations. So, as I mentioned before, variables can have strong associations, but small correlation coefficients. The association is not linear. If we had an exponential graph, it could look very exponential, very strong, clear picture. Correlation would be very weak because value would be correlation coefficient would be very small. There are no, because it's not linear. And lastly, as we mentioned before, okay, correlations are very sensitive to the presence of outliers. The presence of an outlier can affect the correlation both directions, actually. Probably more frequently, the presence of an outlier decreases the correlation factor, but it can be affected both ways. And that's why we said if we are able to, or we think the outlier is significant enough, we can calculate the correlation factor both with the outlier and without the outlier. Okay, and the last thing, and I know I stressed this before, correlation and causation. Whenever we see, especially when we see a strong correlation, it's tempted to explain that the explanatory variable causes the resultant variable. But understand, correlation does not equal causation. Does not equal causation. Okay, scatter plots and correlations can never prove causation. I'm not saying causation isn't present, but the correlation in the scatter plot is not the evidence that shows that. Because very often with a scatter plot, there's a hidden or a lurking variable, something that might be behind the relationship and is actually simultaneously affecting the other two variables. Okay? So we're looking for a relationship. We can see that there is a relationship. One variable can predict the other variable, not causes, can predict the other variable. But in fact, it's neither variable that is actually causing that relationship. There's something in the background. And we'll probably have to look at that a little more depth as we continue to explore this. So ladies and gentlemen, that is correlation. I've made two guided practice examples where we're going to be done with two separate variables, just so I can keep these videos a little bit shorter and be able to explain them more. So your next thing is to move on to example A.